Hi, this is John Whitaker for the Mathematical Analysis 1 class, and this is our 12th video lecture. And last time we ended with our first bit of information about topological spaces, and we had a bunch of definitions that we had listed, and we want to continue that list. So let us recall the definitions that we had, and we're continuing them. And so here we're going to let X be a metric space then we had this note that all points and sets mentioned below are understood to be elements and subsets of X The last definition we had in this sequence of definitions had to do with what it meant to be an open set, and that was that every point of the set was an interior point. And now we want to give a definition in our text that was G. It's something we had talked about before in terms of set theory, but we're going to write it down. It says the complement of E is, and this book denotes it by E with superscript C, and it's given by E complement is equal to all the little x in big X such that X is not in E. And so we'll look at an example. Okay. So if we look at E being equal to, in the real number, the subset from minus infinity up to 1, that's open here, then E complement would be equal to the set having 1 up to infinity. Next definition we're going to give is that of a perfect set. So E is perfect if E is closed and if every point of E is a limit point of E. So that's what it means to be perfect. And here's some examples. So the set of natural numbers is not perfect. It was a closed set, but it doesn't contain, but not every point that it contains is a limit point. It doesn't have any limit points. Okay, that's 1, 2. The set minus 1 to 1, where we include minus 1, 1, is a perfect set. And a last example, if you look at the segment minus 1 to 1, that is not perfect. Okay? And that minus 1 is a limit point of that set, but it isn't contained, so it's not closed. Next definition I want to give is that of a bounded set. This is the right definition. It says a set E is bounded if there exists a number. It's going to be positive. We're saying it's a real number. It's going to be positive. And a point Q that's in X, or metric space, such that the distance between P and Q will be less than M for all P element of E. So that's what it means to be bounded. And as an example, the set -1 to 3, not including -1 or 3, is bounded. Often, we take the Q in the real number system, we take it to be 0. We talk about, well, we look at all the points in here as distance from 0, and the maximum distance is 3. And so M equal to 3 would work if our Q was 0. But I did something a little different here. I said, if we let, you don't have to let Q be 0. What if you let Q be 1? Then the distance between P and Q will be less than 2. And that's for all P element of -1 to 3. That's my first example. My second example is that the set -1 to infinity, I'll just make this plain, is not bounded with our usual metric being the absolute value here. It's not bounded. It's what we call unbounded. Okay. The next definition is that a set E is dense in X if every point of X is a limit point of E or is a point in E, or both. And it turns out, as examples, Q is dense in R, and J is not dense in R with our usual method on the real numbers line. Well, I want to use these definitions now to progress to some theoretical facts. And so the first theorem we'll write up has to do with neighborhoods being open. So here's the theorem. It says every neighborhood is an open set. Okay. So here's the proof. And I'm going to draw a picture to kind of describe what this is saying just a second. But we let X be a metric space, P be an element of X, and, R be greater than 0, and D be a metric, be the metric, on X. Okay. Let E be equal to the neighborhood of P with radius R. Okay. And what we're going to do is show that this is open. Okay. So pictorially, what we have here is, this is my space X. It looks like this. This is a point in it. Here's the neighborhood about it. So that consists of all the points of X whose distance from R is less than P. And if you take some point in that, what I'm going to be able to do is get some little neighborhood about it that will be contained in this n sub R of P, thus meaning that every point of the neighborhood of radius R about P is an interior point of that neighborhood, and thus the neighborhood with radius R about P is going to be open. So that's the kind of picture here. I don't know how well it's showing up, but I'll draw it just very quickly again. Here's P. Here's the neighborhood about it. And you give me some point here, I can draw another neighborhood within that bigger neighborhood. Okay? That's what's being said. All right. So to show that n sub R P is open, I've got to show that every element of it is an interior point. So we're going to let Q be an element of n sub R of P. Then what we know is that the distance from P to Q, by this definition of what it means to be in this neighborhood, has got to be less than R. And so that means that the distance from P to Q has to be equal to R minus H for some H that's greater than 0. Okay? So its distance, whatever it is less than R, and so it's R minus H for some positive H. What we're going to do is we're going to consider all points S element of X such that the distance between Q to S is less than H. Okay? Think about all these points. Really what that is equal to, if you will, a set, I'll call it script S, which is a neighborhood of radius H about Q, what I should say. Okay? So it's a neighborhood of Q. Okay? And what my claim is that neighborhood is going to be contained in the neighborhood of radius R about P. And so here's what I'm going to say. I'm going to say let's say S sub 1 be an element of this n sub H of Q. Okay? Then, so this is an arbitrary element in this set, in this neighborhood. Then, let's look at the distance between P and S sub 1. Well, that's going to be equal to, it's going to be less than or equal to the distance between Q
let's see, it's going to be the distance between P and Q plus the distance between Q and S sub 1. And that's going to be strictly less than, this is R minus H is what it is, but this is going to be less than H, okay, which equals to R. So S is an element of the neighborhood of radius R of P. And so what we've shown is that you give me any arbitrary point in the neighborhood of radius H about Q, then it was a point in the neighborhood of radius R about P. So that means that this neighborhood is contained in the neighborhood of radius R about P. And so what we've produced is a neighborhood contained in this neighborhood. So that means that Q, neighborhood of Q, is contained in this other set. So Q, I'll write it over here. It says that Q is an interior point of M sub R of P and okay, or E. Thus, this neighborhood has to be open because Q is arbitrary point of this guy. So what we're saying is that every point of this guy is an interior point of this set. And that's the definition of what it means for a set to be open. Okay. Next is a theorem that we want to state and prove. It says if P is a limit point of a set E, then every neighborhood of P contains infinitely many points of E. Remember, to be a limit point means that every neighborhood contains some point different than P of E. So this proof, we're going to do it, and it's going to be a proof by contradiction. So let's start off by noting that. Okay. So let P be a limit point of E, okay, then we're trying to do this by contradiction. So suppose, remember what we're trying to prove is that every neighborhood of P has infinitely many points of E. Well, let's suppose the opposite of that. The opposite of that is suppose there exists a neighborhood of P that contains only finitely many points of E. Okay. So if we look at this neighborhood, let's call this neighborhood something first of all. Say n sub r of p. Then, if we look at n sub r of p, now it intersected with E only has finitely many points. So let's intersect it not with just E, but with E minus the set that contains P as well. So it's going to have only finitely many points. And let's call those points Q1, Q2, up to Qn. Okay? All right. Now, what we're going to do is we're going to, since there's only finite many of them, we're going to let r sub 0 equal to the minimum over 1 less than or equal to m less than or equal to n of the distances between P and Q sub m. Okay? So you look at all the distances between P and these points, take the minimum of them. Now, since none of these points are RP, that means that their distances here are always going to be positive numbers, so the minimum is going to be a positive number. Okay? Okay. So here, that's just something I'll write down. Note the distance between P and QM is always greater than 0, as QM is different from P. So what that says is that R naught is going to be greater than 0. Thus, when you look at this neighborhood, okay, it contains R naught. Okay? It contains no point of E, because the points of E that were in N sub R that also were in E besides possibly P itself were just those Q sub I's that ran I running from 1 to N. And this neighborhood of P won't contain any of those because its radius is too small. And so what happens is that this is a contradiction. So we have found a neighborhood of P that does not intersect E except possibly at P. But this is a contradiction because P being the limit point of E, and remember what it means to be a limit point of E, that every neighborhood of P would have to intersect E at some point besides P. But here's one that doesn't. So that's a contradiction. So we must have assumed something wrong. So what we assumed, we didn't make a mistake in our logic. So what we assumed that must be wrong was that there exists a neighborhood of P that contains only finite many points of E. So it must be the case that every neighborhood of P contains infinitely many we're going to look at a corollary of that, a fact that just results from that theorem immediately. So it says that any finite point set, any finite set, has no limit points. Okay. And the proof is by contradiction. Okay. So we start by letting E be a finite set. And then we suppose E has a limit point. Say, give it a name, call it P. Okay. Okay, so what we do is we let R be greater than 0, consider that a radius, then N sub R of P contains, from the previous fact, infinitely many points of E, and that's a contradiction. This is E is finite. So it doesn't have infinitely many points. Okay. So that's that proof. Okay, next I'm going to look at a more of a set theoretic fact. And here's what it says. It says, let A be a set. It's going to be our indexing set. Let the collection of E sub alpha, alpha element of A, be a collection of sets. And we're giving them names, E alpha. Okay? Then, if you were to union up over all the alphas in A of the E sub alphas, and then take that complement, that would be equal to the intersection over all the alphas in A of E sub alpha complements. So union them up, then take the complement, that's equal to the intersection of the complements. So we want to show this these two sets are equal. The way we need to do that is show everything in the left-hand set is contained in the right-hand set, and everything in the right-hand set is contained in the left-hand set. Here's the process. We let X be an element of this union. It's complement. Then, so that means that X is not in the union of the E alphas, so it's not in this set. So that means for every alpha element of A that X is not an element of E alpha, because if it was in one of the E alphas, okay, then it'd be in the union. Okay? It's not. So I didn't write the right thing. It's not in the E alpha. So for every alpha element of A, X is an element of E alpha complement. So if there's not any alpha, it's got to be its complement. And so X is an element of the intersections of all the alphas in A of the E alpha complements. Okay. And so we have proven that the left-hand set is a subset of right-hand set, because I've taken an arbitrary point from the left-hand set and shown it's in the right-hand set. Let me just write that up. So, this union of E alpha's complement is a subset of the intersection of the E alpha complements. Okay, now we want to show the reversed subset relationship. So here, suppose or let Y be an element of the intersection of these E alphas. This is alpha's element of A. Alpha's an element of A. Complement. Okay. So, for each alpha element of A, what we know is that Y is an element of E alpha complement. Okay. So, for every alpha in the indexing set, Y is not an element of E alpha. So, that means that Y is not an element of the union of the E alphas. Because it's not in any of them. So when you union them up, you still didn't get Y. So where's Y? Y has to be in this union. Its complement. Okay. So what we've just shown is that this intersection of the E alphas, tick mark should be there, complement, as alpha runs from all over A, is going to be a subset of this set. So the union of E alpha, its complement. Thus, since we've shown both subset properties, we have that this union equals to this intersection. And that's what we wanted to show. So that's the proof. Okay, I want to look at a relationship between open and closed sets now. And so here's a theorem. It says a set E is open. We're in the metric space here, okay? It's open if and only if its complement is closed. So it's an if and only if statement, so its proof is going to have really two parts. We're going to have this direction. So we let E be open. And we want to show that E complement is closed. Okay. All right, so since E is open, then every point of E That's what it means to be open. Okay. So if we let x, this is a little x, if you will, not our metric space, but let x be a limit point of E complement. Our goal is, we want to show that x is an element of E complement. That's how we show that E complement is closed. It contains all its limit points. That's what we want to show. Okay. So here's what I'll say. Then, remember, x is a limit point of E complement. Then, every, I'll say, R neighborhood of x contains a point of E complement, and you know, it's not E. I mean, that it's not X. Okay. So no neighborhood of X can be a subset of E. So that means X is not an interior point of E. And remember, E is open, so that means that only thing that E contains are interior points. Everything it contains is an interior point. So that means that X cannot be an element of E. And if X isn't an element of E, then X must be an element of E complement. So X was an arbitrary limit point of E complement, and it's in E complement. And so that means that E complement contains all its limit points. So E complement is closed, because that's what it means to be closed. That's half the proof. Okay. Now we want to show the second half. That is, we're going to show, we're going to let E complement be closed. Okay. We want to show E is open. Okay. And so what we're going to do is we're going to let X be an element of E. So it's not the same X I had before, it's just some guy in E. And our job is, we need to show X is an interior point of E. So to show that X is an interior point of E, let's write that out. We want to show and that would mean that E would have to be open, because any arbitrary element of it would be an interior point, and that's what it means for E to be open. How do we show that X is an interior point? That is, we need to find a neighborhood n sub r of x that's that little x, such that this neighborhood is a subset of E, totally contained in E. Okay, so what are we assuming? We're assuming x is in E. So since x is an element of E, x is not an element of E complement. And what was E complement? E complement was closed. And what does it mean for E complement to be closed? Well, it means it contains all its limit points. Well, it doesn't contain, E complement doesn't contain x, so it must be the case that E complement, or it must be the case that x is not a limit point. So let me write that down. So x is not a limit point of what? Of E complement. Because if it were a limit point of E complement and E complement being closed, it would have to contain x. But it doesn't contain x. It's a limit point. Thus, there exists a neighborhood of, let's give it a name, n sub r of x, such that n sub r of x n sub r of x does not contain a point of E. Okay. And that's because of x not being a limit point and x not being in E complement as well. So that means that n sub r of x is contained in E itself. So x is an interior point of E, and since x was an arbitrary element of E, so E is open. And that proves the theorem. We'll look at a corollary of this fact. Here's what it says. It says a set, big F, is closed. Set big F is closed if and only if F complement is open. So here's the proof. Let F be closed. Now consider F complement, okay? Now here's the first thing I want us to know. Note F complement okay, is equal to F. That's kind of a claim here, but I'll prove it very quickly. If you let, so in parentheses I'll prove this. If you let X be an element of F complement, then that means that X is not an element of F complement. So X is an element of F. And if you let X be an element of F, then X is not an element of F complement. So X is an element of F complement's complement. So these show that these two sets, these two lines show that these two sets are subsets of each other, and that's why this is true. Okay? Since F is closed, since F complements, F complement's complement equals to F, then F complement is closed. And so what we know is if the complement of a set is closed, then that means that F complement is open. That's by the previous fact. And then going backwards, if we let F complement be open, okay, then F complement is closed by the previous fact, and so F complement is F is closed, and so that proves it. All right, ladies and gentlemen, there are lots more facts here to prove about topological spaces, and what I'm going to do is at least write up one fact that has several parts, and we'll prove one of the parts. So here's the theorem. It says for any collection of sets, we're going to call them script G of alpha, and these are going to be open sets. Okay. This is part A, I should say. Then the union over all these alphas of G alpha is open. So any union of any arbitrary union of open sets is open. That's what this is saying. B, for any collection script F alpha equal to this collection of F sub alphas of closed sets. Okay. Then the intersection of the F sub alphas over all possible alphas is closed. A few more parts to this statement. So for any finite collection let's say G1, G2, up to Gn of open sets. You look at finite intersection of them. That's going to be open. And finally, part B, for any finite collection, let's say F1, F2, up to F N of closed sets, then their union is closed. All right, ladies and gentlemen, we'll do one part here. Let's prove part A. And then we'll call it quits. So here, proof, we're going to do part A. We're going to let G sub alpha be a collection of open sets. We want to show that their unions is open. That means we want to show that their interior, that every point that it contains is an interior point. So we're going to start off with let X be an element of this union, over whatever alpha is. Then what does it mean to be in a union? You're at least in one. So there exists, I'll say an alpha naught, such that X is an element of G sub alpha naught, since G sub alpha naught, this particular is an open set, X is an interior point, of this set. So there exists a neighborhood of X that's contained in this G sub alpha naught. So this neighborhood is going to be a subset of the union of the G sub alphas. Okay? And so that means that we have found a neighborhood of X contained in that union. So that means that X was an interior point of that union. Wrong. So X was an arbitrary element, and so we've shown every arbitrary element of this union is an interior point of this union. So that means that every point in this union is an interior point. So that means that this union is an open set. And that proves the first part of it. Okay, we'll pick up here next time. Thank you very much.